electrical drawing. So most of you have been made familiar with wiring diagrams, right? And you've seen ladder diagrams, and you've seen schematics, and you've seen one-line diagrams, right? Pretty much all four. Those are pretty much the four. So today's objectives, should you choose to accept them, are to recognize electrical terms, symbols, and abbreviations, define and draw electrical one-line diagrams, define, draw, and troubleshoot electrical ladder diagrams, define and draw electrical wiring diagrams, and define electronic electrical diagrams. The ones that we're going to use the most in this class, per se, are going to be the wiring diagrams and the ladder diagrams. That's the two that you're going to use the most. Ladder being the majority of it. 11 and 15, right? You guys should have 11 and 15. Did you print out 11 and 15? Should have. If you didn't, you need to. Anybody remember this page in the book? It's like page number, I don't remember what page number. Chapter 2. For those of you that read chapter 2, which is none of you. You should be starting to become familiar with some of these symbols. I don't know how well you can see them, but you have push buttons down here, normally open, normally closed push buttons. You have selector switches, you have disconnects or circuit breakers, and you have solid state devices. Everybody kind of remember those a little bit, teeny tiny bit, maybe? Has anybody not seen any of these symbols? Okay, good. Moving on. Recognize and identify all of these. Recognize and identify all of these. So the big one is going to be these motors, right? Single phase motor and Y delta motors. We're going to talk about those a little bit later on, but the motors are going to be in there. Also transformers with iron cores and air cores. The big one's going to be these dual voltage transformers. You guys should have seen a dual voltage transformer by now, right? Anybody not seen a dual voltage transformer? Yes. Yeah, on the other side in Langenberg. Yeah, all of those are pretty much dual voltage transformers, right? You can wire them up for high volt or low volt. 480, 240, 240, 120. Everybody on the same page? Good deal. So, there are a whole bunch of abbreviations. And we're not going to go through all the abbreviations. You'll pick those up as we go. There are four basic types of electrical diagrams or electrical drawings. They are one-line diagrams, ladder diagrams, wiring diagrams, and electronic diagrams or electrical schematics. I call them schematics. Okay? One-line diagrams, sole purpose in life is to do what? Yeah, show the path, right? It's going to use a little bit of symbolage, but for the most part, it's just showing you where it starts and where it ends. Okay? It doesn't give you the grand detail or the grand tour of how it's going to work. It just shows you the start and the end. And we usually use it for service, right? We're describing where the power is coming from and where it's ending up, so that normally we can turn it off. That's the big thing with a one-line diagram. How do I turn this thing off if I need to? Because that's a big thing when you go to lockout, tagout, or try to de-energize something, is knowing where it begins, right? If I need to service this piece of equipment, I need to know how to turn it off. Well, if I don't know where the hell it gets turned off at, it's going to be kind of hard to turn it off. Ladder diagrams are used for what? Anybody know? PLCs. Not only PLCs, just troubleshooting in general, right? Ladder diagrams are used for troubleshooting. They don't give us an idea of how the thing is physically wired, or even in the order that it's wired, right? It just gives us an idea of what it takes to turn this on. That's one reason why we use them in PLCs, is because it's about logic. This has to happen in order for this to happen, in order for this to happen, in order for this to happen, right? So if this isn't happening, there's only a few things that will stop this from happening, this and this. Then I can kind of narrow down my search or narrow down my troubleshooting to what is actually keeping this from happening. Does that make sense? Okay. Wiring diagrams are used to actually wire the damn thing up. How do I wire this up? You go from terminal 13 on the relay on wire number 7. It starts out as wire number 7, goes to terminal 13. It comes out of terminal 14 and becomes wire number 8. Wire number 8 goes to terminal A1 on another relay, right? That shows me physical locations, the actual terminals. Most times it'll tell me the wire number, and most of the time it'll tell me the wire color, the gauge of the wire, and all the information that I need to know in order to physically wire it up. That's what a wiring diagram does for me. And then a schematic usually shows component level material, right? It shows resistors. It shows capacitors, inductors, all the small component level stuff, maybe even on an integrated board or an integrated circuit. Okay? Small level stuff. Most places, most people, most techs, we don't troubleshoot down to the component level anymore. Right? We take the whole board and throw it in the trash, we get a new board. That's what we do. Right? We don't rebuild VCRs anymore or computers. We throw them in the trash and we go get another one because it's actually more expensive to have you take it apart and hook it up to an oscilloscope and try to figure out which component failed. It takes longer to do that than it does to just order another one. And it's more expensive and more costly. So electronics, they're kind of going bye-bye. You're not gonna try to figure out which diode failed. Okay? So this is basically what I just said, right? A one-line diagram uses single lines and graphic symbols to indicate the path of a component's electrical circuit. One-line diagrams are used for information about the circuit, but details of the actual wiring connections and the operation are not given. It doesn't matter what the operation is. It doesn't matter what it's doing. All I need to know is point A to point B. That's what a one-line does. This would be a good example of a one-line diagram, right? Starts at bus number 2, goes through a transformer. That's what it looks like. There's a switch gear. This is all inside this one switch gear. Goes through, looks like a little nice switch here probably, and then goes to pump B. Different pump, different pump, different pump, different pump. Doesn't say what it's doing, right? It doesn't say where it's going. It just says where it started, where it's going to end up. Doesn't say what pump B does. It's just saying giving power to pump B. This would be another example of a one-line diagram. A little more adventurous, right? A little more detailed. Same thing though, one line. Down to here. Ladder diagrams, they're a little more fun, right? Ladder diagrams are what you're going to use to troubleshoot all this stuff, more than likely. Okay? I have a different way of doing ladder diagrams. Because I'm borderline retarded, I think of it as a game or as a puzzle, right? If you draw a little Pooh Bear, right? Pooh Bear is at the beginning of that line. It's a maze, right? Pooh Bear's got to get over here. There's a little jar of honey on this side. How does Pooh Bear get from one side of this to the other side, right? There's obstacles in his way. What are the obstacles? I have a limit switch right here, right? That's what that drawing is, or that symbol is. It's a limit switch. Limit switch looks like number 3 LS. I can't really read it. Yeah, number 3 LS. Number 3 limit switch has to close, or what? Number 3 CR contact has to close, and number, what is that? Number 9 CR contact has to close. So I have 2 paths. Pooh Bear can either go through here, through that contact, or there, this way, right? To get to that honey. Which one? Well, let's say this one closes. Now I need this to close. Now Pooh Bear can get to the honey. It's that simple. And I never understood it, right? It took me like 4 years of beating my head against a wall trying to troubleshoot ladder diagrams before it finally made sense, right? I was always worried about what kind of switch it was. Is it a pressure switch? Is it a float switch? What kind of switch is it? Doesn't matter, right? It doesn't matter if it's a contact. It doesn't matter if it's a limit switch. It doesn't matter if it's a selector switch or push button. What do they all have in common? They got to close. Yeah. Make it close. It doesn't matter what causes it to close. It just needs to close. Once it closes, Pooh Bear gets his honey. That's all his life. That's all he wants to do is get to the honey. So all you got to do is get that and that to close, or, right, because it's in parallel, you got to get that and that to close. Well, how do I get that to close? Well, this limit switch is physical. There's a mechanical something that has to close that limit switch, right? A cylinder, a hydraulic cylinder has to go forward, or a conveyor belt has to hit a certain spot, or a chain has to hit a certain spot, or something has to be moving and get to a certain spot to move that limit switch. Once that limit switch closes, bang! Now I got to get number 9CR to close. Number 9CR is all the way down here. This is number 9CR. Well, number 9CR has to close. What has to happen? Well, I have to hit the start button, but also one of these two contacts have to be closed. One of these two contacts have to be closed. This contact has to be closed, and these can't be opened. Makes sense, right? Pretty great. I love it. Like I said, I treat it like a game. How do I get Pooh Bear to the honey? Then it's just a maze. It's like those mazes you played with when you were a kid, like 5 years old, and just trying to get Pooh Bear to the honey. Ladder diagrams show electrical logic. They're used for troubleshooting. Ladder diagram is used to show the relationship between circuits and their components, but not the actual location of the components. Wiring diagrams, electrical schematics. Wiring diagrams look like this, okay? If you've ever worked on heating and cooling or HVAC or anything like that, they give you this. Literally. I don't have a good one. Usually they teach HVAC in here at night, and they're usually a good one. This is what they give you, right? To get your furnace to come on, all this stuff has to happen. They show you like this. Freaking mystery to me. I don't understand this. I understand this. This is a pain in the ass to troubleshoot. This is super easy to troubleshoot, right? Pooh Bear's got to get to the honey. This, I don't know where the honey's at. I don't know where Pooh Bear's at. I don't know anything. I got to stare at that for 4 hours before I'll figure that out. We use this for troubleshooting, but if I had to wire this up, I know that I have to run a wire from whatever this terminal is right here back to this relay. Right? That's how I wire it up. This, I don't know. Actually, how to wire it up. But being able to go from this to this, or this to this, is important. You got to be able to identify and plan it out. And that's kind of the difference between a wiring diagram and a ladder diagram. And then electronic symbols, like I said, a schematic shows components. Usually in, like I said, in integrated circuits or on boards. Anybody remember what that is? No. Oh. Transistor, yeah. Transistors, that's a potentiometer right there. That's a rheostat, resistor, transistors, diode, all that good stuff, right? Like I said, if you ever have to, chances are you'll never have to troubleshoot something down to the component level. Almost never. You're going to figure out which board it is, and you're going to throw it away. Especially like in PLCs, an I/O board is going to go out, right? You're going Something's wrong with the PLC. Ooh, no. You're going to go out there, you're going to open the door, and one of the I.O. boards is not going to have any lights on. Right? All the other I.O. boards are going to be blinking at you. Blink, 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 blink. There's going to be one I.O. board that's just completely black. You're going to, I better know which one it is. You're going to pop it out of there. You're going to pop a new I.O. board in there, and it's going to go, ooh, it starts lighting up. Fixed it. I'll be in my office if anybody needs me. You're going to walk away like a friggin' wizard because you identified the one board that didn't have any LEDs on it. But that's about 50% of your job. Right there. Hey, something's wrong with that machine. This is what it's going to be. You're going to be sitting in your office, half asleep, and you're going to get a call on the radio or on your phone or over the intercom. It's even better. Come to whatever line. Cool. So you grab your, if it's a really big plant, you have your little three-wheeled cart or your little friggin' Cushman scooter or your friggin' golf cart, and you hop in like Dukes of Hazzard. You come sliding in. Stop the gas, and you go. Or you got to walk down there. Well, I had to walk. So I had a backpack full of tools. There's a Hello Kitty backpack, actually. Hello Kitty backpack. Go walking down there, and they're like, hey, the operator, whose chances are aren't that smart, they're going to wipe the drool off their chin. So I pushed the button like I'm supposed to, and it didn't go brrr like it normally does. Okay? So when I pushed the button, it didn't do that. Okay? So what do you think's wrong with it? I don't know. Did you try pushing the button harder? No. Try pushing the button harder. That's one of my favorite tricks. So they'll go back and they'll be like, it still doesn't work. Okay, I'll take a look. So shut it down if you can. Pop open the cabinet, the main cabinet, or wherever you're looking at. Or you go, more likely, you're going to go into the diagnostic screen on the HMI. You're going to be able to see the HMI. It's going to tell you what isn't running, right? And you're going to be able to go into the ladder. You're going to look at the ladder, and you're going to say, well, the main isn't freaking coming on, right? There's something, one of these inputs isn't going to true, one of these outputs. So this output isn't going to true. None of these outputs are. Well, that's kind of strange. You know, all the outputs can't be off at one time. That's kind of nuts. Okay. And you go back to the side where the PLC cabinet is, you open up the door, and there's one I.O. board, one I.O. rack, and just completely black. No lights on, no nothing. Well, that can't be right. So then, you're looking at it, and you're like, well, you just pop that one out and pop a new one in. You go back over, you look at the PLC, the ladder, everything's freaking green light now. Hey, cool. I fixed it. Shut everything up. I'll be in my office. Back on your cart, like Dukes of Hazzard. Go get lost for like an hour. It's great. It's a beautiful thing. I used to carry a Harry Potter wand in my bag. So, like, tap it. Like, fixed it. Ooh, you look like a god. Realistically, all you did was just look for LEDs that weren't blinking. Troubleshooting. Ooh. Sometimes it's not that easy, but it can be literally that easy. But what I'm getting at there is you're not going to take that board out and try to figure out why they're not blinking, right? You're just going to throw it in the trash and replace it. Your chances are you're going to have another one on the shelf. Does anybody remember what the 5 rules of ladder logic are? Did they teach you what the 5 rules of ladder logic are? They're supposed to teach you that in the second semester. I know I taught you that. Most of you guys didn't have the second semester. There are 5 rules of ladder logic. There's 5 rules of Fight Club, right? First rule of Fight Club is you don't talk about Fight Club. First rule of ladder logic is 1 load per line. Why do we only put 1 load per line? You may know. Why is that a rule? Because I said so? Why do we only put 1 load per line? Kinda. So what happens to 2 loads in series to the voltage? What? It divides the voltage, right? Voltage adds in series. So if I put 2 loads in series, if I have a 24 volt system, each load, if they're equal in resistance, is going to get half of the voltage. Can't have that. It needs 24 volts to run, right? So I can only have one load per line because I need to have the full amount of voltage going to the load. If I put them in series, they won't have the full amount of voltage. What happens to voltage in parallel? It stays the same. So I can put as many loads in parallel as I want. They're always going to get 24 volts, or whatever my voltage is for my system. That's why we can only put one load per line. What's the second rule of Fight Club? Anybody know?
Still talking about Fight Club.
We don't talk about Fight Club. That is right. The second rule of ladder logic is what?
One load per line.
No. All loads are connected to L2. Unbroken chain to the ground or to the neutral or to negative. Okay? With one exception. The one exception is overload relays for motor starters. Okay? Because we want to be able to kill it, definitively kill it, when we have a motor overload. So the one exception is overload contacts on a motor starter. Everything else is never, any other control device is never connected to L2. L2 is usually the neutral or the negative or whatever you want to call it. Okay? Everybody got that? Okay. Rule number 3 is, anybody know? All control devices are connected between L1 and the load. That control devices meaning things that will control the current. Switches, contacts, buttons. All of that stuff needs to be connected between L1 and the load. Not between L2 and the load. Anybody know what number 4 is? Remember? Oh. That's the side of the day at T-Rex. Number 4 is all lines have to be numbered, which I have a little bit of problem with that because there is a difference between a line and a rung, and we're going to talk about the difference between line and rung here in a second. But all rungs, I want you to put rungs, all rungs need to be numbered, not necessarily lines. Okay? This said each line, but I like the word rung better. Does anybody know what the difference between a line and a rung is? Yes?
Isn't a rung an option?
No. A rung is a specific command. Okay? The way that I was taught is a rung has to be SAD. S-A-D. Okay? This is great. You're going to love this. SAD. SAD stands for signal, action, and decision. Okay? In order to qualify as a rung, it has to have a signal. The signal comes from L1. So most lines also come from L1, right? It also has to have an action. What is that action? Typically, it's something has to open or something has to close. Some sort of control device. Some sort of action has to take place. And then a decision has to be made. It needs to turn something on or turn something off. Energize or de-energize. True or false, right? A decision has to be made in order for it to be a rung. So, for instance, if I were to draw a ladder, real quick and sleazy here, all of those are rungs. This is rung number 1, this is rung number 2, this is rung number 3. Why? Because there is a signal, there is an action, and there is a decision being taken place, right? But, let's say I just have like a solid state device wired up high. right? There really isn't an action or a decision taking place on that line. Does that make sense? There's nothing for me to do on that line. There's nothing for me to investigate. Okay? There's a signal, but there really isn't an action or a decision. The decision's made for me as soon as I turn the power on. So what I'm getting at is I need to have numbers for these because something's taking place that I need to look at. This might not need a number. Okay? It's a subtle difference, I guess. It's probably semantics, but it's the way that I would call it. Anti-semantics. I love that joke. Nobody gets that.
I got it.
You got it. Anyway, and rule number 5 is the numerical cross-reference system has to be used. The numerical cross-reference system is to tell me what line the action, right, and the decision, so that decision could affect other lines. If the decision is affecting other lines or other rungs, I need to know what rung they're on. That's the numerical cross-reference. You guys remember all that now? Ringing bells? Okay. So, simple ladder diagram, one load per line. Why? Because voltage. Okay. One load per line. All loads connected to L2. L2, unbroken chain, except for what? Overload contacts on the motor starter. You have to have those. All control devices connected between L1 and the load. These are all control devices. Why are they control devices? Because they either stop current or allow current to flow. That is their job. Okay? Each line should be numbered, which I say each rung should be numbered. Each rung should be numbered and numerical cross-reference. So this action is causing this decision, right? There's a series of actions on this line, or on this rung, right? Signal, action, decision, but that decision is causing actions on something else. The decision here to turn on the forward control relay, or the forward motor starter, is causing action to take place on 2 and 3. Everybody understand that? So then we got to look at 2 and 3 also. That's going to be an action that is caused by that decision. That is an action that's caused by that decision. Okay? If there's an action being caused by a decision on another rung, we need to know where it's going to take place. Most of the time when you're troubleshooting this, you won't be able to hear like the motor turn on. Or you won't even be able to tell that the motor turned on. You'll have to take it for granted that the motor turned on. Why? Because that coil pulled in. Well, how do I know that coil pulled in? Well, because that closed and that opened. Right? And I can troubleshoot that electrically. The motor might be 500 feet away on the other side of the plant. I don't know if that motor turned on or not. But what I do know is that that closed and that opened. How can I tell that? Because I will have access to either side of those contacts. And I can measure them for voltage. Or I can measure them for continuity. Make sense? So I know that that coil is working properly because those contacts closed. And I can measure it. I don't know if physically that motor turned on, but I do know that the coil is working. Theoretically. Okay? And I can measure, we're going to go over a lot of troubleshooting later on too, but I can measure to make sure that coil is getting energy. If I know that coil is getting energy, then, and those contacts are pulling in, chances are the thing's working, right? Now it's a problem with the motor. Everything else is good. We didn't have a problem with the motor. And we're going to talk about that later on when we talk about troubleshooting. So ladder diagrams are read top to bottom, left to right, right? Just like a book. Current has to flow from left to right. Pooh Bear, right? Pooh Bear in his little jar of honey. Pooh Bear starts here on line number 1. And he's got to get to the honey over here on the other side. How does he get there? The only thing that's stopping him is this little bridge right here, this open contact, or this open button. One of them's got to close. Doesn't matter which one. One of them's got to get Pooh Bear to the other side. So we're going to close that one because that's the pilot device. That's allowing me to actually interact with the circuit. I push it. Now Pooh Bear goes to the honey. Bang! Right? Now he has a signal, an action, and a decision. The decision was to turn on motor starter number 1, M1. Well, that causes a lot of other stuff to happen, right? A whole lot of other actions are going to take place. That's going to close, that's going to open, that's going to close. Now Pooh Bear's got more paths he's got to go. There's more jars of honey. So, Pooh Bear starts here. He can't go through there because that's now open. He was being able to go through there. Now he can't. Now he can go through that one, though. So, green light's on until I hit start. As soon as I hit start, green light turns off, red light turns on, stays on. Motor comes on, stays on, until A, I hit stop, or B, I have an overload. Pretty simple, right? Great. Get Pooh Bear to the... This was a little harder. This is a little harder. We're going to talk about these later on. So we talked about troubleshooting. I'm not going to beat this to death, but I do want to hammer on this a little bit. So when the start button is pushed, the motor turns on, but the red pilot light doesn't. What can be the problem? What stops Pooh Bear from getting to the honey on the red line? The motor came off.
Oh, yeah, that's right. Come on. The relay?
The relay, yes, but only one part of the relay, right? It doesn't say anything about the green light turning off, right? But I'm going to assume it's turning off, but the red light just isn't coming on. So what stops Pooh Bear from getting to the light? It's either this contact or it's a bad light, right? How would I troubleshoot that, though? We're going to test, let's say we can test voltage, right? If we're allowed to test voltage, we can test voltage on this circuit. Real simply, right? If I measure from here to here, from the outside of that rung, from that point to that point, what should I measure? Voltage-wise. What? Voltage. Whatever the source voltage is, right? 240 volts, 120 volts, 24 volts, whatever the source voltage is, because that's the whole circuit, right? So if I measure from left side to right side, I get 24 volts. Let's say it's a 24 volt system. Now I keep this lead right here and I move to this point on the contact. What should I be reading? Still the 24 volts. Why? Because it's attached to that point. It's the same point. If this is closed and I move to this side of the contact and I still have my lead here, what should I read? 24 volts if it's closed, like it's supposed to be. If it's open, I get 0 volts. That tells me the contact's not open or not closed. But let's pretend it is, right? Let's pretend it is closed. And when I measure from this point to this point, I get 24 volts, right? That means I should have 24 volts here. If I measure from here to here and I don't have 24 volts, I have an open wire between them. But let's assume I do have 24 volts here. Okay, why is that light not coming on? It's something screwy. So if I measure from here to here and I still have 24 volts, I just got a bad bulb, right? I have an open across that bulb. Bad bulb. But I can find that real quick. Just bing, 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 bing. There's the open. If I had an open right here, measuring on this side of the contact gives me 24 volts. Measuring on this side of the contact gives me 0 volts. Real quick. Boom. There's my open. Measuring from here to here would also tell me that. Right? I would see, if you see source voltage or close to it, where there shouldn't be, you have an open. What do you need to have in order to have voltage? You have to have resistance. Voltage only appears where there's resistance. You have to have resistance. So if you see voltage, if I measure across this wire, there should be no voltage there, unless it's extremely long, right? Extremely long, 100 feet long. I might see a 1 volt drop, right? Voltage drop. But theoretically, I shouldn't see any voltage across that wire. But if I see voltage across that wire, that's an open wire. Or an open contact, or an open terminal block, or a bad terminal block, right? We have a bad connection. You gotta start thinking about this stuff. This is fun for me. Like, I love this kind of stuff. Okay, let's try this one. The motor won't run in either condition, either direction. Why did I say condition? What do you think it is? Neither one of these will energize. What do they both have in common?
Non-gain energy.
Stop and slow
Yes.
press.
What control device do they have both in common?
Stop and start.
Well, the stop button would keep both of them from coming on, right?
They both have limit switches.
Yeah, but what are the odds that both limit switches are in the open position at the same time? Probably not very good, right? So, I don't believe in coincidences and stuff like that. I wouldn't necessarily go to that first, right? But there are two things that both of those have in common, right? The overloads is in common to both of these rungs, right? And the stop button is common to both of these rungs. So if both motors won't turn on either direction, that tells me it's either the stop button, which could very likely be, right, or the overload. Now, theoretically, yes, both of those could be in the open position. Theoretically, both of those contacts could have failed at the same time and opened up. Pretty far jump, right? That's not where I would start. If it ain't this, and it ain't this, right? If it's not the overload, it's not the stop button, then yeah, we're going to have to dig deeper. But chances are, it's that guy. That's where I would start. Because that's another one of those cool things, right? You walk out, the thing won't run, you push the reset on the overloads, it goes click, and it starts running again, right? Now you look like a wizard again, because you just expecto patronum, right? Pow! Drop the mic and walk away. How does he always do that? Because you start out with the simplest thing first. It has to be one of these two. If it's not, then we got problems. It's called Occam's razors. Anybody ever heard of that? It's because you guys didn't go to real college. That's like freshman psych, right? Occam's razor. The simplest answer is normally the correct answer. Simplest answer is what? That guy. And it'd be really easy to check, right? Because from here to here, if I push that forward button or the reverse button, I should get source voltage, right? If I go from here to here and I push the button, I should still get source voltage. If I don't, that's open. Or I can go from here to here and see if I get source voltage. If the stop button is closed and the overload's closed, I should still have source voltage. Make sense? It's great, isn't it? It's a beautiful thing. Beautiful thing. Super neat. The motor will run in reverse, but not in forward. What do you guys think it is? So forward will work. Or wait, reverse will work, forward won't. What do you think it is? What could it be?
Forward button.
There's only a couple things, right? The forward button, or the forward limit switch, LS1, or that, right? That reverse, the normally closed contact on the reverse start. There's only really three things. Because we know it's not the stop button, right? How do we know it's not the stop button? Because it'll run in reverse. We know it's not the overloads. Because it'll still run in reverse, right? So it's got to be something on this rung keeping Pooh Bear from the forward contactor, right? Pooh Bear can get to the reverse contactor, but he can't get to the forward. So the only thing it could be is whatever's on that line. If the start button's actually physically working, if the forward button physically makes contact, the only thing it could be is one of these two normally closed contacts here that aren't closed. Or, worst case scenario, we got a bad coil, right? If all of the control devices check out okay and we're still good, we got a burned out light bulb. We got a bad coil, which can happen. Not normally. It's usually the last thing. Make sense? You guys excited about this crap? I don't know why I'm the only one that gets excited about this crap. I'm weird, I guess. Yeah. Yeah, that's 90% of your job is right there. Grabbing the schematic, looking at the ladder diagram, not the schematic, grabbing the ladder diagram, looking at it and go, what can it be? Narrow it down to 2 or 3 suspects, go out, check it. If you're really good at narrowing it down, using logic to narrow it down, that's when you can walk out there and hit one button or friggin' tap the side of a button. Hey, it works now. Right? You look like God. Because, like I said, the operators are just going. All I ever see him is walk around, and then when he finally comes out and does something, he like taps it with a hammer and walks away, and it all of a sudden starts working. Yeah, I know, it's cool, isn't it? And I make like 3 times as much as you do. See ya. It's a beautiful thing, man. It is. Alright, let's move on. You guys are getting bored. Okay, let's answer some questions. Could we... we'll put all of them on there. Who's primarily responsible for your safety? You are. What are the 4 basic types of drawings? One line. Ladder. Wiring diagram, and schematic or electronics. What is ladder diagrams good for? Troubleshooting. Oh, we skipped number 3. How many lines are on a 1-line diagram? 1 technically, but as many as you need to show the path. Okay? Technically, it's 1 line from source to end result, but there are multiple quote-unquote lines. So, again, splitting hairs. What are the 5 basic rules of ladder logic?
1 load per line.
1 load per line.
Loads connected to L2.
All loads connected to L2 with one exception, which is overloads. Number 3 is what?
Control devices are only between L1 and
Yep, all control devices are mounted between L1 and the load. Wire numbers. And yep, all lines going to be numbered and
cross-references.
yeah, numerical cross-reference. That's the 5 basic rules of ladder logic. Another name for simple or basic motor control circuit is what? We haven't really talked about this during the PowerPoint, but the most simple motor control circuit is called a start-stop station. Right? Start, stop, start, stop. That's about the most simplest way you can turn on a motor. 3-wire start-stop station, or just start-stop station. Okay, that first diagram that I showed you that had a start-stop button and a motor starter, that's a 3-wire start-stop or just start-stop. What is shown on the wiring diagram?
Position of components.
Yeah, the physical location, the physical position of the components, and the relationship to everything else. What type of solid-state components are on an electronic schematic? All sorts of stuff, right? Diodes,
Capacitors.
transistors,
LEDs,
capacitors.
EVRs.
Yeah. You can have integrated circuits, IC chips, right? Which drawing type has a line and wire reference numbering system? We're going to say, well, and wire reference. Yeah, I guess you can have, ladder diagrams can have wire reference systems, yes. We're going to say ladder. Wiring diagram can have line numbers and wire references also, but they usually don't. Questions? When do you need your electrical tools? Every dang day. You ranking material?
Does shock boundary depend on the current going through the device?
The shock category?